Hello everyone. In this video and the next three videos, we are going to talk about different robotics aspects of the Baxter robot from Rethink Robotics. In this one, we're going to talk about this forward kinematics and Workspace. The next one about this inverse kinematics. The next one about the Jacobian singularities. And finally, we talk about the resolved rate method. Okay. So this redundant robot, Baxter, that has 7 degrees of freedom and all of them are revolute joints, was developed by the company Rethink Robotics. And it is what we call a Cobot. Okay, that's another term that you might hear somewhere. Cobot means a robot that can coexist with human beings or live together with human beings. So if you hear this term somewhere, Cobot, you know the meaning of it. And why is it called like that? Because really it was supposed to be trained by humans, and humans really take the robot arm and move it to any configuration, any pose that they want, and then to another one and do some task with it. And the robot is supposed to really keep in mind all of these configurations and how it went from one to the other, and then be able to repeat it, right? So you could then train this robot, add a gripper or anything to the end effector, right? To the the last link, the joint, the frame 7, and perform any task that you want. So here is the robot. Now sometimes the robot has 2 arms, sometimes 1. In this case, it has 2 arms. Each arm has 7 degrees of freedom, and we call it redundant because, you know, in order to achieve 3 positions and 3 orientations at the end effector, you really only need 6 degrees of freedom of the robot. So when the robot DOF goes beyond 6, we call it kinematically redundant. And this one has 7 degrees of freedom. As I said, all joints are revolute joints. Now, if you have 2 arms, clearly now you have 14 degrees of freedom. The head here that has a camera and a monitor also has 2 degrees of freedom, and it has a pan and a tilt. So in general, you might go up to 16 degrees of freedom. It was made by the company Rethink Robotics that, as far as I know, went out of business. And now this robot is still being managed and basically, I'm not sure if it's manufactured anymore or not, but if you need your robot fixed or something, a German company bought the Rethink Robotics. So if you have this robot in your lab, I know we have one in our lab, you still can send it to Germany if you need some repair or something. But it didn't go super successful, although it was a very good robot, I would say. At least for some mundane task like this one here. You see the robot is trained, and on one arm you have a gripper, on the other arm you have basically a link that can push, and it is being trained to make a coffee for you. Okay, so here we go. And the other one I can show you is this one. And you can see here the kids at the school, they are training it to kind of do some, I would say it's like dancing basically. So you see the kids are just grabbing it and moving it, each arm separately. And it is trying to keep in the memory what has been done to it. So now you see, it is exactly repeating those motions for you. And it's kind of like dancing or so, huh? So it is a really good robot for education, for some, I would say, basic assembly task or some mundane task, daily task, right? This robot was a very good robot. And in this first video, we are going to talk about the parameters of the links, the values of the joints, how far they can go, the limits, right? Learn about the DH parameters, the Navitt-Hartenberg parameters of the robots, find the A matrices, and show you how we can perform forward kinematics, and also finally, how does the workspace look like. Now I have written some functions, some Matlab functions for this that I'm gonna upload, and you can find the download link in the video description. Okay, so keep an eye for that. Now, a couple of important things. One is the material that we're using in this video, this publication by Dr. Williams from Ohio University, which is published in April 2017. This is a very good and comprehensive overview of this robot. Dr. Williams has done an amazing job, so we are going to borrow the material from this publication. The other thing is I also going to show you the SolidWorks model, which is made brilliantly, and it, as you can see, it only has one arm, not two. This is a different version of this robot. And this robot has a bunch of different buttons that you can push for training, for capturing images, and so on. This is your monitor, and it has 7 degrees of freedom. So the good thing with this assembly, you can move it and you can see all the 7 degrees of freedom. So this is one, right? So the 7 degrees of freedom, as also mentioned in this paper, we call them shoulder roll, right? And shoulder pitch, the first two. The next two we call them elbow roll and elbow pitch, and the last three we call wrist roll, wrist pitch, and another wrist roll, which is basically the spin at the very end, right? Theta 7. So this is this robot. This is the SolidWorks model. I'll tell you where I found this model. I didn't make it. So this is that shoulder roll. This is the next one, the shoulder pitch. Then we have the basically elbow roll. Then we have the elbow pitch, right? Then we have the wrist roll. Then we have the wrist pitch. And finally, we have the last wrist roll, okay? So these are the 7 degrees of freedom. Now, if you can see here, this robot has sensors here. It has a camera in the middle of the monitor, and there is a camera down here too. There is more. This robot is equipped with lots of sensors, especially a lot of cameras. Okay, if you want to know where I found this, all you need is to go to Google and then search on Google, basically, grab CAD Sawyer robot. That's another name this robot is known with. So let me just show you. And as you know, GrabCAD is a website that is a file sharing of different CAD software, right? CATIA, SolidWorks, Fusion, so on and so forth. So if you want, just go to this link. As long as you are signed up in GrabCAD, which is free. If you haven't done it, I absolutely recommend go do it. There are tons and tons of free, amazingly modeled SolidWorks, CATIA, and so many other CAD files that you can download. And you can get the complete model of this robot from this website. This is where I got the model, and then I exported each model as an STL file that later I can read into Matlab in this function here. As you can see, I'm going to read those STL files exported from SolidWorks, and I can basically apply the joint values to it and show you the animation or a drawing of the robot in Matlab as well. Okay, so these are two good resources about this robot if you're interested. As I said, this publication here and that model in GrabCAD. Okay, so now we know about this robot. It is time to look at the details of it. First one is DH axis and DH table. As I said, there is one for the right arm, there is one for the left arm, and although they are very close to each other, but they are not identical. This robot has a bunch of parameters, L0, L1, all the way to L6, as well as 3 other parameters that we'll see later, small h, capital H, and big L. Okay, these are all the distances on the robot that are fixed, and we have the exact numerical values for them. And it has 7 joint angles, as we know, theta 1 all the way to theta 7. Okay, so The other thing we are going to use in this lecture, we're going to use modified DH parameters. As you know, Denavit-Hartenberg has the standard, and it also has the modified DH. And if you are not sure about what is the modified one, because what you read probably in your textbook or you have seen in my previous videos, that's the standard one. There is also one called modified, and I have published a video on that recently. So if you see this video that I published recently, it says modified versus standard DH. So if you are not familiar with modified DH, please go and watch this video. Okay, this will tell you about modified, but the original videos that I published on forward kinematics using Denavit-Hartenberg, let's see if I can find them for you. Analytical forward kinematics. Here. You see, it says using DH convention. Both of these are the standard DH. They are not modified. If you want to know modified, which I'm going to be using, please watch this video that I published recently. So if we go with the modified DH, these are the axes that you have for frames basically 0 to 7, right? So you can see frame 0, frame 1, right? And you see they are kind of on the top of each other. Then you have frame 2, you have frame 3, 4, 5, 6, and 7, right? And you can have an extra end effector here for which the frame is different than frame 7. Right now in this Matlab function that I have written, I'm going to neglect this final end effector frame. I'm going to go only from the very bottom of the robot, which we call word frame. It's not even this frame BR. It's below that, I'll show you. I'm going to go from there all the way up to what? To frame 7. So at the moment, I'm not going to consider an extra frame for the end effector. I assume my end effector is frame 7, which is not really the case, but let's say it's just like a camera or something attached to it. So if I use the right arm, then these are my DH parameters, right? And my joint variables are, of course, theta 1 to theta 7. For the second joint is theta 2 plus 90 degrees. Remember in DH conventions that each x is perpendicular to the previous z and is intersecting it. That's still the same for modified DH. The only difference is that the axis of rotation and the origin of frame I is on joint I instead of the next joint. And the order of the 4 parameters is rotation x times translation along old x multiplied by rotation along new z and translation along new z. While in the standard one, if you remember, it's rotation z, old z, followed by translation old z, followed by translation new x, followed by rotation new x, right? So it's rotation z, translation x, rotation x. That's the standard. While in the modified, it's rotation x, translation x, followed by rotation z, translation z. So both of them are rotation translation, and the order is xz instead of zx. So the A matrix, which describes each frame with respect to the previous one, comes from the product of these 4, which is this guy, as you can see, based on the 4 parameters, theta, d, a, and alpha. Which again, if you're using a right arm configuration, these are the parameters for the right arm. If you're using a left arm robot, these are the parameters for left. And if your robot has both of them, then you have to use both. Okay, so these are the DH axes, and these are the DH parameters. And I assume you know, once you have determined the axis, how to fill in the table. So I'm not going to explain each and every one of these terms. And again, if you look at these 2 tables, you'll see that they are identical, right? I mean, look at the alphas, look at the A's, look at the D's, look at the thetas. You see they are the same thing. It's just the reference point that is different, whether it's on the left side or the right side, but the tables are the same. And the way that the axes are basically situated with respect to the original one is also the same. Again, it's whether this, you see here the Z3 is on to the left or to the right, but you see the X3s are the same. So they are symmetrical, as you can see here. Now, the parameters here, L0 to L6, the numbers for them, as I said, are shown in this table. And L6 is the parameter that I'm not going to be using in my Matlab function because, again, I'm not going to be using the end effector. I only start from the world frame, which, as I'll show you, it is here at the very bottom of the robot. And I go all the way here to frame 7. And if there is any gripper or anything, I would neglect it. So I go and determine the position and orientation of frame 7 with respect to the world frame, which is at the base and the bottom of the robot. Okay, so this parameter L6, as you can see, which is this length from the gripper to the intersection of or to the origin of, let's say, frame 6 and 7, this distance I'm not going to be using in my calculations. But if you want, you can add that, right? You can add also a matrix from frame end effector to frame 7. So that's the only parameter I'm not going to be using. The other parameter that we need to talk about is L0, which is the offset between the origin of frame 0 to this frame here called BL or B right, the base of the right frame, right arm, or the base of the left arm. Okay, this distance L0, right, which is the height 270.35 mils. This will show itself in the A matrix that describes frame 0 with respect to the frame base. And this frame base, still, it's not my world frame, okay? This frame base, as you can see in this picture, this frame base is here, okay? It is at the base of the arm. Basically, it's like my shoulder frame. And that base frame here that you can see in this picture, this base frame is not on the top of the world frame. It's where the arm starts, basically, whether it's the right arm or whether what? It is the left arm. So that frame, with respect to the world frame, which is at the base, we describe it using 3 distances. One is this height h. So those base left and base right are a height h above the origin of the world frame. Also, from the center of the robot to the shoulder places, you have distances of L to the left and right, and then they are a little bit behind the robot for an offset of small a. So you need these 3 parameters, right, if you want to describe the frame BR or BL, the shoulder centers, with respect to the world frame, right? So overall, there are 3 parameters here, and as well, there are 6 parameters here. As I said, I'm not going to be using L6, but anything else, I have to be what? I have to be using in my forward kinematics. So that's the only one I'm not going to be using, right? Anything else should be used in our forward kinematics. Okay, so let's look at my A matrices, which describe each frame with respect to the previous one. But before that, let me warn you that these joints are all revolute joints, but it doesn't mean they all go one full rotation, right? Or sometimes you see some of them go 2 full rotations, like in the Skera robot. If it's 4 degrees of freedom, the last rotation typically can go 1 or 2 rotations. So not in this case. If you look at these joint limits, they are none of them is like negative 180 to positive 180. None of them is like 1 full rotation, right? The best one that can get very close is like 350, right? Joint 5 It can almost go one full rotation, but not completely. Joint 7 also, which is the last spin, basically, it can almost also go one full rotation, right? But there is like joint 4 that can only go 150-degree range. And these are all designed so that the robot's parts do not hit the other members, the other links, right? So they are used like basically like to avoid collisions, right? So each joint has some limitations. So when you want to do forward kinematics, inverse kinematics, determine the workspace, and so on, you have to keep all of these limitations in your mind. Okay, so as we said, each A matrix is the combination of a rotation X, old X, followed by translation along old X, followed by a rotation of the new Z with angle theta and a translation of new Z with distance D. If you multiply this together, you get this homogeneous transformation matrix, right, where each 3x3 first minor of it is the rotation matrix of frame I minus 1 with respect to I, and the fourth column, elements 1 to 3, these are the positions of origin of frame I minus 1, or I actually, with respect to I minus 1. It's the new frame with respect to the old frame. Right? So now if we plug in the values from each rows of the table, let's say I'm using the left arm configuration. If I go and plug in these four numbers for A, alpha, D, and theta into this formula, that gives me this rotation, this homogeneous transformation matrix, A of 1 with respect to 0. If I use the second row, then I get A of 2 with respect to 1, and so on and so forth, all the way to I go I of 7 with respect to 6, because there are 7 rows here in this table, as you can see. Right? So that way I can describe now what with respect to what? I can describe frame 7, which is here, with respect to frame 0, which is here. Right? If I multiply all of those A's together, if I multiply A of 1 with respect to 0 pre-multiplied by 2 with respect to 1, 3 with respect to 2, all the way to 7 with respect to 6, I can finally get what? A T matrix of 7 with respect to 0, which, as I said, is like A of 1 with respect to 0 times A of 2 with respect to 1 times all the way times A of 7 with respect to 6. But that's not enough. Remember, frame 7 is with respect to 0, not with respect to the world frame. So what we need is to add what? Some 2 extra A matrices to take us to the world frame. And what are those? One, as I said, you have to go from the frame 0 to the shoulder center, frame B left or B right, for which the major parameter is this parameter L naught, right? And as you can see, their Z's of frame 0 and BL are aligned, and their X's are aligned, and their Y's are aligned. So the only parameter that you will see in the A matrix from 0 to BL or BR is really L naught, right? So let's go ahead and look at that A matrix here. So this is this guy here, as you can see, right? And you see the rotation matrix is an identity matrix because the axes are aligned, and the only offset you have is a Z offset with amount L naught that you can clearly see. It's aligning this Z to distance L naught. So you need that A matrix as well. Now when you pre-multiply all of this, correct? If you pre-multiply all of this with that A matrix, what you get? So you have A of 0 with respect to, let's say, B left, Now you go from 7 to B left. But again, B left is not your final frame. You need to go from B left to what? To the word frame. And this is your B left here, and this is your word frame, and you need these three distances. So we need an extra A matrix, and this is your extra A matrix here, which will take you from BL frame to the word frame. There is a rotation of 45 degrees involved, as you can see, right? Clearly you see these axes of B left and the word. There is a rotation involved, as you can clearly see, right? You can see here, this frame with respect to this one, there is a rotation Z of 45 degrees, which includes this rotation matrix, and then you have offset along each one of the axes X, Y, and Z of the word, which are described by L, negative H, and big H. Negative small h and big H. So that is your A. So now if I pre-multiply that final A, then this is what you will get here. So BL with respect to word. If I pre-multiplied with everything, now the product of all of these 9 A matrices will give me what? The T of frame 7 with respect to what? The word frame, which has the rotation matrix of the frame 7 with respect to word and the position of it in the word frame. And I showed you all of those 9 matrices. One of them is down here, as you can see. One of them is this guy, and the 8 other matrices are these ones, as you can see. So all you need is really to basically multiply these 9 A matrices together. And as I told you, since the left and the right matrix the parameters of the left and right configurations are the same, so all of these 7 matrices are the same. Also, going from frame 0 to B left and B right is the same. So 8 of the 9 A matrices are the same for left and right. The only time you see a difference is here, going from B left or B right to the word. That's the only place you see a difference, and the difference is here. There is a negative here, there is not here, it's positive. Here there are 2 negatives, here this is positive. And here there is negative L, this is positive L. So in 3 places, 3 signs are different, but everything else is exactly the same for left and right arms. Good. So now I assume we are ready to look at the code and draw the robot for different angles. One thing I want to mention for you is when all of the joints are at 0 angle, right? The robot looks like this. The arms are stretched all the way back and behind the robot. So while all the joints are 0, it's like you who have opened both of your arms and stretched them behind you. This is the front of the robot, this is that monitor, this is the back of the robot. Right? So the robot is stretching its arm behind it when all of the joints are 0. So if you want to make sure that your code works fine and shows the robot properly, set up the angle so that when they are all 0, the robot is showing itself like this. And let me show you in my code here. So this is the code that performs the forward kinematics for the left arm. You pass to it all the 7 joint angles, and then it takes all of these parameters. It forms all of those 9 A matrices that I showed you, and then pre-multiply from BL with respect to word all the way to 7 with respect to 6. And it gets you frame 7 in the word, and then it gives you the rotation matrix and the position vector. Here, if you want to make your code better, you can apply some conditions and say, let's say if Q1 is not in the joint limits, right? Remember, we have joint limits here. Or Q2 is not in the joint limits, Q3 is not in the joint limits, and so on and so forth. If any of the values that you provided is outside these limits, it can what? It can give you an error message and say, out of joint limits, please enter a new number and terminate the program, right? So I can do that here for you as well. Okay, so here I have added all of those, and if any of these conditions is violated, it is going to assign empty to the outputs. It is going to display out of joint limits, and it is maybe I can add something. Please try again, right? And ask you to try again with values within the joint limits. But that's it. And if that's not the case, if all joints are within the range, then it is going to read all of these numbers. The only number that I have not used is L6. I can put it basically a comment because I'm not using a separate end effector. And here, let's call this function. So one time I call it with all joint values of 0, which are within the range. And you can see this is the rotation matrix of 7 inward, and this is the position of 7 inward, right? And if I now use, let's say, this joint 6 is between -90 to 120. So if I give it, let's say, 150, it should not work. And you see it is giving me the appropriate message and it is not returning anything. So this is the function for performing forward kinematics, right? And this is the other function that I wrote. This one reads the STL files exported from Solidworks from this model. It reads those. And then here, I'm not using all of those A matrices in a perfect one-to-one match. The only reason I'm not doing it is when you bring the STL files into Matlab, they are not necessarily centered at origin, and you also need to do the assembly of the members as well. So you see here, I'm doing some stuff here after bringing them. This is to center the axis of rotation, their z-axis, to center all of them at the origin. If you don't do that, assembly of it is going to be way harder. So here first, when I bring and read them in using this function called STLRead, I make sure that it can really center them at the origin. You might say, where did you get these numbers? Well, I determined them by basically looking at the red STL file and looking at the location of the axis, and basically I found them all manually. Okay, so there is a lot of work gone into this, and then here, to a huge extent, I'm using those 7 A matrices, right? But I'm using some offsets here and some angles. I have to add some extra values to them. So I make sure that at the 0 configuration, the robot is stretched back like this. So I have to do a little bit of modification. Again, that's the way the STL files are read into Matlab. And some manually found numbers to do the proper assembly. So once I read those, and then I use the patch command, and from the transformed values of the points, right here, when I read the joint values 1 to 7, I transform all of the points using the homogeneous transformation matrix. If the point belongs to link 1, then I only transform them with A1. If the link belongs to the point belongs to link 2, then I have to multiply it by A1 and A2 together. If it belongs to link 7, then I have to use all 7 of the A's to transform that point of belonging to link 7, right? So you transform all the members using the appropriate product of A matrices, and then using the transformed points and using the connectivities, right, which comes from here. When you read STL files, you read the points and the connectivities, or which 3 points should be connected together to form a triangle, because STL files is literally a bunch of triangles. Use the connectivities, use the vertices that you have transformed, you give your faces and edges of the triangles some color. Here I'm giving different colors to different members, but I'm coloring all of the edges with color black. Use the patch command, and for my operation here to perform, I need two functions. One of them is the translation function that I need in several places in order to bring them to the origin, and that small function here I wrote it. And the other function I need is STL_read, which is basically I'm going to upload for you, as well as this Baxter function, this utility function STL_read, which I have not written. It was on MathWork shared website, file sharing website. This guy I'm gonna also upload for you, so you can run this function, right? So you call this function. It is not supposed to really return anything, just to draw the robot for you. So here I'm going to call this, and I'm gonna give some numbers to my joints. Let's use all zeros for now, and let's draw the robot. Okay, there we go. So this is your robot, and you see this is the base, this is joint link 1, this is the monitor and the pedestal, joint 2, 3, 4, all the way to joint 7. You can zoom in if you want, right? So this is your robot. These different members are colored differently. And you can rotate this if you want. Let me zoom out a little bit. Now the STL files are coarse. They do not have a ton of points on them. If the STL files were really heavy, it is going to be even slower than this. And you can click on any point that you want and use the data cursor, and you can get the coordinates of it, right? So use on this data tip or data cursor, click on any point, and you see you can find what? There are X, Y, and Z points. If you want, you can click on this end effector and so on and so forth. Good. So this function, if you now use, let's say, a separate set of joints, let's say you want to rotate the first joint by 50 degrees, and let's say the fourth joint by 20 degrees, the sixth joint by 10 degrees, this one maybe by 60 degrees, then it can replot the robot at those values for you, right? So now you clearly can see how the robot has changed its configuration. Right? So here we go. And if you want, you can keep calling this function with different joint values, and even you can use it for animation. So you can write a simple script and do an animation using this function here. And if you want to accelerate your animation, I suggest you take this part of this function out, put it in your script. So each time you call this function, the reading of these 9 STL files does not happen each time in the loop, because that is gonna make your animation function very slow. Okay, so make sure you only perform this reading of STL files one time, not in a loop in the animation. But I'm going to share this file as well as this STL_read and this forward kinematics for you. And this is another one in which you can do look at the workspace. Now, of course, since you have 7 joints, even if your joints have 10 points within the allowable space. So as you go from -141 to 51, you sweep this 190 degrees range with only 10 numbers. So 10 numbers for joint 1, 10 numbers for joint 2, all the way to 10 numbers for joint 7, then the number of points that's for which you have to call this forward kinematics and get the end effector point is going to be 10 to the 7 or 10 million. And you can see here these 7 nested for loops in which I have to keep calling what? Keep calling this forward kinematics. And it is going to make it very slow. So here I use that, and I use a scatter plot to show you the workspace, but every time I'm running it with any number 4 or above 4, it takes forever for it to basically generate the scatter plot of the workspace. If you're asking about the workspace basically looks like this. If you use some very high fidelity computer and let it run for some good time, the workspace looks like a crescent, I would say. This is the side view of it, and this is the top view of it. Now here, one color is the left arm, one color is the right arm, right? So if it's like this arm here, you can clearly see. Right? So this is from the top, this is from the side. And this is what this robot can achieve. So it's not like a hemisphere or something. It is a complicated kind of crescent shape, 3D crescent shape that looks like a crescent both from the top and from the side view. Again, this is published in this PDF. So you can go down in this PDF and look at more plots of the workspace if you're interested. You see green one is for like, one of them is for right arm. I guess blue is the right and green is the left. Good. So this is how this robot's workspace would look like. And again, here, this is the script I have written for it. So look under the video description, you'll see the link for all of these. And for the draw, it's not going to be just the draw and the STL. It is going to also include these STL files. So I will upload it as a zipped folder. So look for a zip folder containing these 2 files and these 9 STLs. Look for an individual M file for the forward kinematics and one for Baxter. And I also will give you in the video description the download link on GrabCAD, where on GrabCAD you can go and download this amazing SolidWorks model. So hopefully it was useful to you. And as I said, in my next video, I'm going to continue over its inverse kinematics, Jacobian singularities, and then the resolved rate method. Thank you so much for your attention, and I will see you in my next video. Thank you.